Hey everyone, and welcome to this explainer. Today, we are taking a massive leap. We're going to transition from your everyday, slightly flawed human intuition straight into the universal realities of physics. If you've ever felt like classical mechanics is just this confusing, messy jumble of equations on a chalkboard, well, you are absolutely in the right place. Today, step by step, we're going to break down the actual blueprint of the universe. Here's our roadmap for today's session. We'll kick off by debunking some everyday physics myths. Then we'll dive into the first law, understanding inertia, followed by the second law, force and momentum, and the third law, mutual interactions. Finally, we'll wrap up with the physicist's essential toolkit. We've structured this specifically to build your foundation sequentially, taking you from super simple concepts all the way up to complex interacting systems. All right, let's jump into Section 1, Debunking Everyday Physics Myths. To really understand dynamics, we have to start by busting a pretty massive myth, one that actually dates all the way back to Aristotle. You see, common sense tells us that if you just stop pushing an object, it naturally halts, right? That's our intuitive view. But the true physical reality is completely different. Objects absolutely do not naturally want to stop. They are forced to stop by a hidden actor. Think about a kid pulling a toy car across the carpet. Our brains trick us into thinking the pull is what creates the velocity. But physically, that toy car only stops moving because of an invisible force, friction, aggressively pulling against it. Literally, if we lived in a completely frictionless void, that little car would just keep rolling forever. You'd never have to touch it again. And that realization brings us right to Section 2, the first law, understanding inertia. Now that we've exposed friction as the ultimate buzzkill, we can look at the absolute baseline of reality. This is Newton's first law, the law of inertia. It simply states that an object remains at rest or in uniform motion unless acted upon by a net external force. Honestly, the best way to think about inertia is just physical stubbornness. That's it. Mass is literally a measurement of that stubbornness. The heavier an object is, the more incredibly stubborn it is about changing whatever it happens to be doing right at this exact moment. So whether we're talking about a completely dormant asteroid just sitting there in the dark, or a spacecraft cruising along at 10,000 meters per second, functionally, they are in the exact same state. If the net forces acting on them equal zero, their acceleration is absolutely zero. Without an outside force, their physical stubbornness wins out every single time, and their current speed, even if that speed is zero, is never going to change. So moving on to Section 3, the second law, force and momentum. Because, eventually we do want to shake things up. What happens when we finally introduce a change into that stubborn system? Enter Newton's second law. This provides our catalyst. The law tells us the force is the exact rate of change of momentum over time. A great way to visualize this is to think of force as an invisible push or pull that acts exactly like a currency. It is the literal money you have to spend to buy a change in an object's momentum. No money, no change. But to really grasp this currency, we need to understand momentum first, which is just mass combined with velocity. Picture a tiny, incredibly fast bullet and compare it to a massive, crawling delivery truck. Because of the math, they can actually possess the exact same amount of momentum. The truck has immense stubbornness, but low speed. The bullet has tiny stubbornness, but blistering speed. To bring either of them to a dead stop, you'd have to spend the exact same amount of your force currency. Now let's apply this to impulse, which is just your force multiplied by time. This is where it gets highly practical. Think about a seasoned pro catching a high-speed ball compared to a complete novice. The pro always pulls their hands back, right? They do that to extend the impact time, which essentially stretches out their force currency. The total change in momentum is the same, but by spreading out the time, the peak force on their hands drops dramatically. It saves them from a broken bone. Before we start throwing more objects into our universe, let's look back at our hidden actor, friction. It actually behaves in two very distinct ways to oppose our applied force. First, we have static friction, which cleverly matches whatever force you apply right up until a breaking point. Then we have kinetic friction, which provides a constant, steady opposing force once the sliding actually starts. The friction spectrum illustrates this beautifully. When you look at how force is applied, there's a sharp step function. It reveals a really frustrating universal truth. It is physically way harder to get a stubborn block to start moving than it is to keep it moving. Once you push hard enough to break that static friction threshold, kinetic friction takes over, and suddenly it costs less of your force currency to keep it sliding. Which perfectly sets up Section 4, the third law, mutual interactions. Let's expand our view from just pushing one single block to looking at complex systems where multiple bodies are interacting. This is Newton's third law, action and reaction. The golden rule here is that forces always, and I mean always, occur in pairs. To physically touch an object in this universe means you are instantly and simultaneously being touched back with an equal and opposite force. There is absolutely no exception to this rule. Picture an astronaut floating out in the void, pushing against a massive satellite. The very act of the astronaut pushing on that spacecraft results in a simultaneous, mathematically identical force pushing right back against his own spacesuit. He literally cannot act on the satellite without the satellite acting right back on him. Now, here's where people get tripped up. A smart student usually asks, wait, if the forces are always perfectly equal and opposite, shouldn't they just cancel each other out entirely? How does anything actually move? Well, that's what we call the cancellation fallacy. Those equal forces are acting on entirely different bodies. Because the astronaut has low mass, that force shoots him backward with high acceleration. The massive satellite feels the exact same force, but its immense physical stubbornness means it barely accelerates forward at all. They don't cancel out because they belong to different systems. And this mutual exchange leads to one of the most elegant realities in all of physics. Because these interactive forces are always perfectly equal and perfectly opposite, the total momentum of any isolated system is completely, permanently conserved. Seriously, even after a violent, chaotic, high-speed collision between two particles, if you tally up the momentum afterward, it will perfectly match the total momentum from a split second before the impact. All right, home stretch. Section 5, the physicist's essential toolkit. We've covered some pretty deep theory, so let's give you the practical cheat codes you need to actually solve these dynamics problems on your next exam. Whenever you face a complex physics problem, do not just rely on your gut instinct. Always follow these 3 sequential steps. First, deliberately isolate your specific system from everything else. Second, draw a free body diagram. And third, methodically tally up all your forces to solve for your missing variable. That free body diagram, it is going to be your absolute best friend. By sketching out a simple dot and some arrows, you are completely stripping away the confusing, chaotic reality of physical carts, spinning wheels, and messy pulleys. You're translating the noisy physical world into a pure, clean, mathematical blueprint where you can clearly see gravity pulling down, the normal force pushing up, and tension pulling to the side. Honestly, I want you to mentally bookmark this right here. Take a screenshot of it if you need to. This perfectly consolidates all 3 of Newton's laws into your ultimate conceptual cheat sheet. We've got the physical stubbornness of inertia in the first law, the push and pull currency of force in the second, and the unbreakable mutual interactions of the third. This right here is the operating system of classical mechanics, entirely on one screen. As we wrap up this explainer, I want to leave you with one final, incredibly provocative thought to ponder about the grand clockwork of our reality. If the universe's total momentum is forever conserved, locked in this permanent, endless balance of equal and opposite forces, what does that mean for the very first movement that ever occurred? Who or what provided the initial force currency to set this entire cosmos in motion? Think on that until next time. Keep questioning and keep exploring.